we're going to go into a new topic. Thank you for the donut, whoever you are. Any idea? Thank you. Right, so today we're going to do an introduction of one of the most difficult topic in structure analysis. Okay. So this is nothing compared to Mohs circle. Okay. Mohs circle is straightforward. Tomorrow there will be no lecture. I'll give you all time to study for your term test. So the topic that we're going to cover today is shearing stress due to the shear force. Okay, that's the topic that we are going to cover today. And I believe Dr. Koshi has done a very surface aspect on this topic. Am I right? Can you remember that? Yes or no? Yes. Okay, so he has done a good introduction, I think. Okay, but we are going to go into depth. We're going to go deeper into this topic. And this topic, as I said, is one of the most toughest topic that you'll see in structure analysis. Okay. So the first thing that we are going to look at is there are only two formulas that you will see for this case. Is we have what we call shear flow. And the symbol for shear flow is equal to Q, small q, is equal to VQ over I. Okay, where we have Q, usually known as our shear flow, and the units is in Newton per meter or pound per inch. Okay, and then V correspond to our shear force. And our shear force is in Newton or is in pounds. And then we have Q, which correspond to the first moment of area. And this is in meter cube or in inches cube. And then if we look at Q as a formula is equal to A y bar, okay, where A is defined as the area of interest as in meter squared, and y bar is defined as the distance from the distance between the global and section centroid. And this units is in meters. And I is known as the second moment of area. And the second moment of area, the units is meter to the power 4. So if you look at the shear flow Q is equal to VQ over I, okay, in terms of units, V, which is we define, which is the shear force in meter, right? In Newton, and then we have the Q in meter cube. And our second moment of area is meter 4, so this corresponds to Newton per meter. Okay. So what is a shear flow? Okay, what is a shear flow? So if we have a structure, and this is our X, and this is our Y, and then you have rotation about Z, what you see from here is we have a simply supported beam. At point A, and then we have point B, and then we have a load applied down here, P, and this is our point C. And what we have, the distance from here to here, is our L/2. And from here, we realize that we have reaction forces. So our AY is equal to P/2, and our BY is also P/2. Okay? So when we sketch our shear force diagram, we have a profile that looks like this. Okay, so this is our L/2, and this is our L. How it looks like is we have here to here, we have P/2, and then it comes down by P, and then you have minus P/2, and it finish off here. So from here, we know that our V in our Y direction, or Vy max, is equal to P/2. Okay. The next thing that we are going to do is we are going to look at the cross-sectional area. So now when we are viewing the cross-sectional area, now based on the transformation, this is our Y, this is our Z, and then we have rotation of X. So the cross-sectional area looks like this. And then from here, this is our centroid. Okay. And then we know that over here, this is our Vy, okay, our shear force. So Q, when we sketch Q, okay, it looks like this. Okay. So the length of the arrow correspond to its magnitude of the shear flow Q. Okay. So these are all our Q. So with the name like shear flow, so shear flow is similar to the flow of liquid. Okay. And we know at the top and at the bottom, okay, so these 2 points are known as our terminus. Okay. So terminal can be a plane or point which generate zero shear flow. So at the top and the bottom, later you'll see is where the shear flow is equal to zero. Okay. Now, the next thing that I'd like to introduce to you is shear stress and the formula is shear is equal to VQ over IT. Okay. So the only thing that changes if we have shear stress is we have the what? We have the thickness. Okay. So we have tau correspond to shear stress or shearing stress. And this is in Newton per meter squared or PSI. Okay. And the next thing that we have is T. This corresponds to the thickness of the structure which is measured perpendicular to the shear flow. Okay, to the shear flow Q. So I'm going to extend this formula and I want you to see a trend, okay? So the thing that I like to do now is if we were to look at shear stress, shear stress can be equal to TR over J. Okay, let me do this first, okay? So shear stress can be equal to TR over J, okay? Or plus minus By over IZZ QZ over T plus minus VZ over IZZ, sorry, IYY QY over T. Okay. The plus and minus is dependent on the direction of the shear flow. Okay, it's dependent on the direction of the shear flow. Now, let me elaborate what I mean by that. Okay, so now we have a cross section now. Okay, a cross section. And this cross section has a Vy. Let me draw the transformation first. So this cross section, okay, is under a load. And the load is Vy. And it carries a torque, which is going in this direction, which is Tz. Okay. So we are going to have elements now. Okay, we are going to have elements. So we are going to label this as element A, element B, element C, element D. Okay. So I'm now going to sketch, Okay, I'm now going to sketch the shear flow. Okay, I'm going to sketch the shear flow. Okay, I'm now going to sketch the shear flow. So how does shear flow works? This is how the shear flow will flow. Okay, so it's going to be here. This is how the shear flow will flow. Okay, so these are all our Q. And then if we were to now sketch due to the torque, okay, so the next one that I'm going to do now is due to the torque. The shear stress due to the torque. And the shear stress due to the torque will rotate in this direction. And the shear stress is equal to TR over J. And I'm only drawing at the surface because the shear stress is maximum